So I've talked to so many people here, and there seems to be way more machine learning experts on the audience than us. So it's like we know comparatively little, and I'm going to talk about pretty trivial stuff. But if you have we're going to have lots of discussion later. If you have any good questions, please save them in the end, and I'm sure we can learn more from you than the other way around. So I'm going to talk about today the theme of machine learning and how to apply it to make creative tools for artists and designers.
Can I ask you to speak a bit louder so
Sure.
that I hear at the back?
Okay. So let's introduce ourselves. We work in Google Brain. Google pays our salaries. It's a pretty cool place, and we focus on machine learning research, and they also develop TensorFlow. The most popular open source framework for deep learning. But there's more competitors these days, as I know. The research areas of Google Brain include natural language understanding, like machine translation, healthcare, computer vision, like perception, machine learning theory, we kind of want to know what's actually going on, robotics, and what we're doing, we're focused on music, art, and tools in a project called Magenta. So Magenta is a team within Google Brain. We focus on music and art with machine learning. And it started off focusing on music, creating tools to model initially just MIDI files and piano music. But as we're going to see from Adam later, it's grown to many very beautiful and sophisticated projects, which I'm quite proud of seeing. There's a lot of recent work that we published this year, and I think later on next week at NIPS, there's going to be more presentations that's going to follow. So inside Google Brain, even outside of Magenta, there's been a lot of work that is related to machine learning that can be applied to creativity. For example, colorization is an interesting topic that I find. In colorization, the problem here is to take black and white images and to predict what colors the image would be if it were a color image. So this may seem like an easy problem because we can get infinite training data. We can take any image and convert an RGB image to black and white. But it's actually harder than it looks. For example, for helmets, for football helmets, we don't know exactly what color it should be in, but maybe there's a range of possible colors that we can assign. So some of our work includes this work on PixColor that chooses a set of different modes to choose from. So I think this is an interesting research direction inside Google Brain. So inside Google Brain, there's another research topic that our group did as well called neural style transfer research. I'm sure we've all played with neural style transfer. There's lots of apps that can transfer styles to famous artists. But here, the work is we take a style and we actually try to model a latent space of a style. What this means is, we can take an image of Brad Pitt and find the style of Brad Pitt so that we can find, if we apply style transfer, you get the same image. And if we're able to do that, we can interpolate between this different style. We can interpolate a floating point vector to go from Brad Pitt and choose how much of this artistic style we want. And this theme of being able to interpolate between a latent vector, we find to be quite profound and important for a lot of creative ML tools that we're going to talk about later. So, and as we heard, there's a lot of work at GANs. Ian Goodfellow, who invented GANs, work at Google Brain, and there's so many GANs there that I can't even keep track of. I think there's only 700 possible GAN names with XX GAN. So I can't keep up with the research anymore, but the idea is you can also take a vector, like a Gaussian randomly generated vector, take two of them and interpolate between two different rendered images to get an interpolation between spaces. And in some of these GAN models, you can also encode images. So on the left-hand side, we can see we can take an actual real face and encode it to a GAN version. And then we can take another face and encode it to another GAN floating point vector and then interpolate them. So this interpolation theme that we're seeing more and more of inside of machine learning. So in my own work, in this work, we try to create a generative model for vector images because as a new researcher, it's kind of hard to compete against GANs. So you want to try to find something where there's not a lot of people working on. And also, since like everyone's working on modeling pixel images, we want to try modeling vector images. In this work called SketchRNN, we develop a model that can generate vector images, and you can see here we generate images of cats, stick figures, I think, trucks and insects, and we're also able to interpolate between these images using this method. So this work that we did was inspired by artists. Like, this is my favorite piece from Picasso. So Picasso spent his life trying to understand representation. He'd probably make a good computer vision researcher, but the good thing is, instead he spent his life making beautiful art pieces rather than writing newspapers. And we see on the left-hand side, he starts to draw very realistic pictures of ox. A lot of machine learning techniques now is about modeling realistic images. But what we're more interested in is modeling doodles of ox on the right-hand side. So I think these doodles are special because just with a few strokes, we as humans understand that this doodle is an ox. And I think if we're able to model how people draw doodles, it might tell us a thing or two about how we ourselves interpret what we see in our mental image of the world. So that's one of the motivations for this research. And so the data set that we're going to work with is a data set that looks like these vector images. This turtle is something that I drew. It's not as good as Picasso, but it'll do the job. And we're going to model pictures as a sequence of motor actions of a pen, like their relative x and y coordinates and also the state of the pen. And we're not going to model like traditionally pixel images. So our image model will have to generate these sequences to mimic these vector images. And it's relatively easy to get data sets of pixel images, especially of celebrities or random things, but it's relatively hard to get big data sets of vector images. So luckily, inside Google, there's this game called QuickDraw, launched at the end of last year, which went viral. And thanks to our friends at Creative Lab, they've been able to collect millions of these doodles. And in this game, oh, by the way, if you play this game, I want to thank you for contributing to our data set as well. So in this game, it's kind of fun. It's kind of gimmicky. So the game tells the user to draw something, like a bear. And in under 20 seconds, the user has to draw a bear. And there's a neural network that has nothing to do with our research to tell the user whether it thinks it's a bear or not. But regardless, we get the data, and we've open sourced all of the data. And inside of GitHub, there's around 50 million images of these vector images that we can play with. So we trained our model on the QuickDraw dataset of vector images. So I'll talk briefly about our model. Our model, called SketchRNN, is a variational autoencoder combined with recurrent neural network. Recurrent neural networks because we're dealing with sequences. So when we want to train this model, what we can do is take a training image of this cat here and encode the sequence of motor actions that's required to draw this cat into an encoder RNN. This RNN would output a latent vector, like a vector of floating point numbers, into a low-dimensional vector Z. And then we will add noise to this latent vector, like a typically Gaussian noise in a variational autoencoder, to make it generalize, and so that it can't store infinite information. And when we're actually generating a sketch, we use a decoder RNN, an autoregressive recurrent neural network, to sample each of these motor actions to generate the cats. And we're going to condition the decoder on this latent vector so that it would generate a cat that may mimic the information that's encoded into the training sample. And when we train this, we want to minimize the distance between the output image and the input image, and this can be trained end to end. So after we built this model, we can test it on some examples. Here's a model trained on only the cats. So there's no labels. We just took only the cat class in the data set and trained it. And we can see some examples where if we feed in like a cat with a body and a cat with a head, it generally draws a similar looking cat. But here, like if we feed in like a cat with 3 eyes, for example, like it'll only draw a cat with 2 eyes. So it kind of learned a thing or two about like what a cat should look like. But we just to stress test it, and we don't want it keep an internal lookup table of the most common cats and display that. We can feed in like a toothbrush, and then it'll feed out something that kind of looks like the toothbrush but has cat-like characteristics. So it learns to draw like what the human on a quick draw data set will draw as the essence of the cat, which I thought was interesting. We can repeat this experiment with pigs as well, and we see here it can learn to correct the number of legs of the pig. And if we feed in a truck, it will still draw a pig, but it'll kind of look like the truck. And then we can, because this model is, we can convert the data into a latent space. If we train a model on all of the cats and all of the pigs at the same time, we can even do things like interpolate between cats and pigs. So here we first auto-encode the cat head into a cat and a pig with a body into a pig. So they're not exactly the same. But if we play around with GANs or variational autoencoders, you can see when we can morph between one photo to another photo. Here's an example where we can morph between a vector image to another vector image. So we can see like stroke by stroke how it changes as we interpolate between this latent vector. And we see like the latent vector captures things like the body and whether the face is a cat or a pig. And unlike pixel images, that's more or less smooth. We see more discontinuities when we interpolate this because we're encoding something that's a continuous value, but the decoder is actually half continuous because the pen states, whether you lift up the pen or not, and whether you finish the drawing or not, is discrete. So we see more gappy latent spaces because of that. Here we can also interpolate between trucks or buses and cats to get cat bus, and like the pig and the elephants. This is South Park, anyways, right? And for those of you familiar with Word2Vec, we can do like Sketch2Vec, and we can take away the body of a pig and add a body to a cat by doing vector arithmetic. So it'll be interesting. Like we tried to train this model on all of the yoga drawings. Yoga drawings, people generally draw stick figures, so these are quite easy to model. But when we sample, we don't just take the argmax, but we can control a temperature parameter so that we can control how certain our distribution is or how uncertain it is. And if we make the temperature really low, we get the average yoga pose that people tend to draw in a vector drawing. And if we increase the temperature, we get like these hot yoga, kind of like very chaotic yoga positions with mats. And if we take a few random points in latent space of Z, we can interpolate them and even make an animation. So I like these latent space animations because it kind of tells us the limitations of our model and where it can go wrong. Like sometimes it generates a bag of lines, but sometimes the mat becomes the legs and so on. So there's some creative applications one can use with such a model. Like given some start of an image, we can draw various different gardens, faces, owls, mosquitoes, and trucks, and so on. So it's like a auto-completes for drawings, which, to be honest, I think there's more we can do there. Like I'm personally not a big fan of autocomplete. Maybe we can ignore what it's suggesting and figure out something we want to draw. So here's an example where you can draw like a cloud and it'll draw the rain afterwards by training on the rain class. One of my colleagues, Ian Johnson, he combined this model with an open source program that generates realistic paint, and he's generating these like faces using this JavaScript program. So these faces are generated using SketchRNN. And another gentleman, Alexis, he combined SketchRNN with this edge detector. So if you take a webcam, you point it into the sky, you get clouds, and you draw this little line around the cloud. You can fill in the initial stroke into SketchRNN to generate the cats in the cloud. So I thought that was kind of cool. So we also play with building mock-up apps using this tool, so that on the left-hand side we can draw the beginning of a bug, and it'll finish variations of the bug, and maybe that may provide some inspiration or not. But I think these mock-up tools are useful if we want to play around with how we should use our machine learning tools. So I mean, these don't take that long to build, but I really like the concept of moving machine learning tools into interactive JavaScript so that we can play around with it. Because if you just run a model and you can't play around with it, it's hard to have an intuition of the limitations of the model, and it's hard to be creative to see what you can actually build from these models. So I think like the ability to move TensorFlow or PyTorch models into JavaScript or whatever fast UI framework is quite important for the future. Someone from an art school in New York University Allison took our program, took a model trained on everything, and started generating these abstract pieces, which look kind of funky. Maybe Allison can sell this at some point. And inside QuickDraw, there's hundreds of classes. We try to build models that train on more than one class as well. And if there's a lot of experts here. If you want to play around with the QuickDraw dataset, I also recommend taking similar classes that have similar characteristics. For example, cats, lions, and tigers. Because I found on a cat class, usually you just get heads and you don't get many bodies. But that's opposite from the tiger class. So by taking the different classes, you can get more from training on the QuickDraw dataset. So that's just something I found. Subsequent work, because we put this paper out earlier this year, there's other research groups around the world who played around with the model as well. So this work from Chen's group, they took the model, but rather than doing a sequence-to-sequence model, they use a convolutional network as the encoder. So you can actually feed in a pixelated version of a sketch. And they found this work better. If you use a pixel encoder into a convnet, into your latent space, you can do things like put in Bugs Bunny, Machimarro, and so on. And then you can feed that to generate your latent vector, and from that latent vector generate the nearest, or what the QuickDraw data domain would look like. So these look kind of convincing. I'm not sure if these are cherry picked, but who knows. But like, for example, like the Hello Kitty, they kind of appear the same places with different characteristics, and the Bugs Bunny. So I like the fact that we put this code out and the paper out, and people can take it and extend it and make things better. So here's some prior work I've done before joining Google Brain. So when I tried to learn TensorFlow and RNNs, I was reading tutorials where you can train RNNs to generate text and so on, but I trained a recurrent neural network to generate kanji, or Chinese characters, by studying some free fonts that were available, so that it can hallucinate kanjis that don't exist, like urban sheep, stick stone ladies, and so on. So this work was sort of inspiration from that time. But because now we built a variational autoencoder, we can also now use this model to train again on the kanji and look at the interpolation between different kanji, which was not possible when I first started. Like here, if you're familiar with kanji, there's like the simplified way of writing turtle and also the book, and then it can interpolate between how to write these characters. And when it's writing them in a stroke order, that still kind of makes sense. It's the essence of how people write, from top to bottom, left to right, and so on. We don't really know, this character does not exist, so there's no correct stroke order for that. But the stroke order for the top left and the bottom right is correct. So it'll still write the stroke order of the middle characters, imaginary characters, in a self-consistent way. So I mean, if you train a GAN or a VAE on the pixel versions of these characters, it doesn't have the sequential information. But the good thing about this model is we capture the sequential information, and the latent code would store a plausible way from the data on how to write this. So I think it's kind of good to stress test our models that it works not just for QuickDraw, but maybe it works for kanji as well. And the good thing about the open source community is, we put our models out there. I implemented Alex Graves' handwriting model, and I put out the TensorFlow model, and people do interesting things with these models after you put it on GitHub. Like someone took our model and combined it with an AxiDraw and started generating gibberish, and they call it like a ghostwriter, AxiDraw with a handwriting RNN. And someone else also took the Sketch RNN model and combined it with this low-cost Mural bots, I think it costs less than $100, and then you can generate drawings on the fly and have the robot draw it on a piece of paper. So I thought that was kind of cool. And so we also put all of the code as an open source TensorFlow code in the tensorflow.org domain. But if you're a PyTorch user, there's also a PyTorch implementation as well. So that's it from me. And then I'm going to leave the presentation to my colleague Adam, who's going to talk about his work on music generation. Thank you.
All right. Thanks, David. And thank you for having us. Let me just switch over. All right. So yeah, I'm also work on the Magenta project along with David at Google Brain. I just want to give a little bit more background about Magenta specifically. So our goal is pretty large. We're trying to figure out, we're trying to do fundamental machine learning research, as well as apply that research to the domain of creativity, create actual interfaces that musicians and artists can actually use, and then kind of get feedback from them and iterate from there. So we have a pretty large goal for ourselves, but we think that you kind of have to do all of those pieces to actually make this work. And I think one of the biggest pieces, though, is actually really interfacing with the external community of developers as well as artists. So we have, all of our code goes up on our GitHub whenever it's ready, and we publish everything we can, and I get emails from artists all the time that we bring in and try to explain machine learning to them, usually unsuccessfully, but hopefully, eventually all of our stuff will be easy enough to use that you won't need to know how to, run TensorFlow to do it. So like we like to give this example of we like to give this example of like Les Paul and Jimi Hendrix, and we kind of liken ourselves more on the Les Paul side of, although he himself was actually a pretty incredible practitioner, like we're kind of developing these tools, and we don't actually know how the artist is ultimately going to use them. And so like one of our most rewarding things that could happen, we feel, is if somebody took something we built for one purpose and just kind of like used it for some totally wacky way that was actually really amazing and changed rock music like Jimi Hendrix did with feedback. The original goal for the electric guitar was not for that. It was for just being able to hear the guitar in a large room. So if you're gonna look at music with machine learning in the modern age, I think the first thought is to use something like an LSTM, so recurrent neural network, doing next step prediction. This has been done a lot with text, predicting the next character based on the previous ones. So you can apply the same idea to notes, where given the notes that it's output previously, what should it output next? And one simple way of doing this to model like a monophonic melody is just to output each time step some pitch to start a new note, or maybe you should just hold the previous note you were playing, or maybe you should stop playing anything and rest for this next step. And you could like quantize your music down to like 16th notes or something, right? So that's where we started. And after finding some, scraping the web for every single MIDI file in existence, and then cherry picking our favorite output, we came up with this. Let's see if this works. And then all the record labels called us and were like, so you get, like, it's very, very like elementary, but it kind of gets the essence of like what a melody sounds like, and it's actually really fun to play with. Just having it generate random things or inputting some sequence and then letting it try to continue it. And we built, I'm not going to show all of them, but we built several tools that allow people to kind of play around with that concept. But one thing you might notice immediately is just, oops. I always do this every single time. Okay, is kind of how robotic it sounds, right? And that's for a couple reasons. One is the quantization. So I mentioned like we're quantizing to 16th notes. Also, because we only want to have a single output, like a categorical variable in the end where we're just saying play this note or hold or rest. We can't specify play this note but play it, push the key this hard, or only play it like a slightly before the beat or something like that. So I want to show you an example just like of a nice musical piece that's been destroyed in this similar way. So if you take a good piece of music and you quantize it, this is kind of what it sounds like. And I apologize, I don't know what this is actually. I should probably. Okay, so this is that same piece played by Sagiv Or, who's a member of our team. So this is not an AI playing it, but. So yeah, I want to listen to that one a lot longer because it has that like humanity, that real feel of emotion to it that the other one lacks. So kind of that was like the first battle we wanted to fight, is like how can we kind of get that back? And so Ian, Simon, and Sagiv on our team came up with, it seems like so simple now, but like a different way of representing the output space where now at each time step, at each output step, you're actually not outputting for a specific 16th note. You can actually output, whether you want to turn some note on or you can think of it as pushing the key down on the piano, whether you want to lift your finger off the key, and also how you can also change how hard you're pushing the keys for the next time, right? So one output step, it might say, next time you play a key, you play it this hard, and then it'll tell you which key to play. And then you might also want to advance the clock forward. So now you can get really fine-grained timing information of just a few milliseconds ahead. And you can do polyphony, right? You can push down multiple notes and then move time forward. So let's see. Oh, actually, sorry. One more thing though you need with that is you actually need a different data set, because the data that we scraped off the web, all these MIDI files, most of them are just made by somebody like sitting down with a sequencer and taking their favorite like pop song and making a karaoke version, right? And so it's quantized. They probably didn't do velocities. It's not played by a person, actually performed by a person. But Yamaha was nice enough to. They probably didn't know anybody was gonna do this type of thing with it, but they just took all these performances of people using their Disklavier piano, which is this really amazing. It's a really nice piano, but it also records MIDI, with, really precise, and can play back MIDI too, which is really fun. And they just put a bunch of performances up online in terms of MIDI format, and so we were able to train on that. And then what you get is something. Whenever we now generate from the model that was trained on this data, you get something like this. That's not what I wanted it to sound like. I don't know what's going on there. Let's try this other one, because that one kind of started off bad. So I think you can see there's a lot, I don't need to explain the difference there, right? As far as like that versus the original thing I played you, I think there's a huge amount of progress. One thing that you might notice though is it definitely lacks, the original one I played had a little bit more like repetitiveness. It sounded a little bit more like a song, whereas this just sounds like somebody going off on the piano. And that has to do with the fact that now your outputs are way more dense, right? Like for a given second of music, you have to do a bunch of different outputs to change the velocity, start a bunch of notes, then move to the next time step. Whereas before, it's just 16th notes. So the model could kind of remember a little bit more of what it was doing and was able to then learn how to repeat and things like that. So this kind of lacks the structure that the original model had. And we'll come back to that in a little bit. So these are cool, but right now, so far I've just shown you something where you can like basically push a button and get something out. Our goal is really to provide some tool for musicians to use. So the big question we asked ourselves is like, how can we actually build a model that musicians can control? And we don't want it to be quite that complicated. We want it to be something like this, like just really intuitive, but that anybody can actually combine. musicians are able to take these individually, they're kind of simple, and then combine them in complex ways to make a really unique sound. And that's what we'd like to be able to enable them to do with our stuff. So with this model I showed you a minute ago, the performance RNN, we thought like, okay, well, how can we add some more controls to it? And we came up with a really simple, the most obvious way you would do it is to add some conditioning into the model, so that when you're training it, you're also measuring things like, for this piece of music that I'm training on, how dense are the, sorry, what is it, pitch density? I think that's more note density. So how dense are the notes? How many notes are being played every second? And you can kind of feed that information into the model. And so then at generation time, you can specify, I want you to give me something that's this dense, and that'll kind of bias it towards producing things like it saw whenever you were telling it before that that's what it was seeing. So we built this little interface that some of you may have seen using DeepLearn.js, by the way, which is a really nice web framework that actually does all the inference in your browser. So this thing is just generating on its own from this model, but I can do things like turn up the note density. And you see that it's starting to play a little faster. I can change which key it's playing in based on this pitch histogram. Let me turn this down a little bit. So now it should only play mostly black keys, which it's doing. Right, so this is a little bit of control, so that's kind of fun. But it's still, one of the problems with this type of conditioning is that you have to, when you're training the model, you have to basically decide, okay, these are the things I want people to be able to control, and then train the model with that in mind. Whereas when you're using a latent space model like what David was showing before with the sketch model, you actually have some more freedom to define that stuff later on, which I'm going to talk a little bit about now, how we made that possible. So an autoencoder like SketchRNN is this thing where you're training it. It's sort of two models, right? We have an encoder and a decoder where you give it your inputs, you pass it through the encoder, which produces some small code. So it's much smaller than your original input. So you're forcing it through a bottleneck. It has to learn how to compress the data down somehow. Then you pass it through a decoder, which upsamples it essentially back to the goal, at least, is to get it back to the original input as its output. And so you train this end to end, and you penalize it whenever it does it incorrectly, and just like how you'd use gradient descent to train this. And then in the end, you get this z vector, which essentially is like a point in this huge latent space that represents a given example, and the points that don't align to something that you input also should be something that is in the same distribution as what you train the model on. So one of the other things I didn't mention is this is a variational autoencoder, meaning that we actually also regularize it so that we try to keep the points all within something similar to a normal distribution, or a multivariate normal distribution. So you can think about it as trying to compress all this data down into points that lie within this huge sphere or something. And any point in that space, when you decode it, should produce something like your data that you trained it on. And this will become a little bit more clear later on. But the idea is that when you play in this space, instead of trying to adjust things in your input or output space, you're actually able to control variables that the model has learned are important. And as you saw, like whenever David was showing you with the interpolations, you imagine going from the cat to the pig, there's some dimension of this high dimensional space that whenever you move along it, it's making things more pig-like or more cat-like. The model has kind of learned what that means, even though we can't necessarily define it ourselves. And the goal is to learn something similar for music. So again, the SketchRNN work was definitely an inspiration for the work that I did this last year, which was music VAE. So this is a variational autoencoder that instead of being trained on sketches is trained on sequences of notes. So the first thing I want to show you is doing interpolation with that. And again, if you could imagine this space of all of our points, and if I give it two examples and have it map it into that space with the encoder, then I can move slowly along the points that connect those two points and have it decode and output a musical sequence. In this case, I've trained it on just short 2-bar drum beats and also on little melodies. So this does have the quantization I had before, so you have to forget all that great stuff I said about adding humanity to it. We lost the humanity again, but we have this additional control. So let's first listen to this drum beat interpolation. What you're going to hear first is the 2 bars at the beginning, then you'll hear the 2 bars at the end, and then you'll hear the slow interpolation between them. That's the first one. And this is where we're going. So one thing to note is that this you'll hear it a little bit better in the second one, but in this example, it's actually not just adding in individual notes. You can see that there's actually some that it adds some things in and removes them, because what it's doing is actually trying to produce something that's reasonable under the distribution, and just adding in individual notes isn't always going to be something that the model thinks is reasonable. So now let's listen, and unfortunately the sound's not so great, but let me try to turn this up. Let's listen to an interpolation for melodies. I think you'll definitely notice that a little bit more here. So that's where we're starting. So they're quite different, but let's see if you can hear any large shifts. Oh no. Hang on, back it up just a little bit. So unfortunately, I was kind of, Fortunately, that didn't come across perfectly on the over the Apple TV, but I think you can see from this image that it's pretty smooth, right? Like you didn't hear any point where it just like totally shifted to something different. And so I think this is kind of a cool tool where I can imagine, for example, a DJ entering in like their sequences they want to start their song with, and like here's where I want to go, and then now they have the freedom to play around with all the effects and stuff on it as it's kind of slowly shifting there. And in fact, we kind of have built or working on, this is our early prototype, some interfaces that will allow you to do this using, again, DeepLearn.js in your browser. So let's look at this quickly. So this is using the drum beats, where I can drag this. So in the 4 corners, I just have 4 drum beats that were, these are kind of hard-coded in for now. And then as I move this around, you can see how it's interpolating in the space between them. So we can turn it on. And then I can also, I can generate random corners. So in this case, it's just going to sample 4 points from that Gaussian distribution. So now we have just new drum beats in each corner, and then we can mix them again in this 2D space. And then we can also draw a little path. So we can say, I want you to start there and end up there. And so just over time, it's going to slowly morph as it moves through this 2D space. And so again, this is kind of an early version of it. It's also going to be able to work with melodies as well. And we're, again, hoping that people are going to be able to take this and actually use it to produce music. So we're going to have ways for them to actually pipe this through their favorite production software and use it to compose something, as well as to do a live performance. All right. All right, so then I was also wanting to try to do this with longer sequences than just 2 bars, but it turns out, again, as you saw earlier, like when you start getting to really long sequences, the model tends to forget what it was doing before, and it makes it difficult in this variational autoencoder framework for it to be able to reconstruct something from the input space and the output space if you just use a single LSTM going from end to end. So what instead I did is I built this kind of hierarchical LSTM decoder where you have different clock rates. So the first level, for example, if we want to model, here I'm modeling 16 bars. The first level just outputs 16 embeddings from the latent vector, and then each of those are decoded into a single bar of music. So it's like 16 by 16 here, so you get your full 16 bars. But what's really key here is that you're doing each of these bars, you're decoding it completely independently. So that no state is passed from one bar to the next, and that forces the latent vector to model the long-term structure of the music instead of just some local rules for it to follow. And this gives you a much better outcome in terms of getting repetition and getting something that doesn't just wander around a theme. And so I want to play you some examples of that. Actually, first I want to mention one other thing you can do, which I quickly tried, was instead of just sending this second level embedding to a single LSTM, you can send it to 3 separate ones that are each trained on a different instrument and kind of model the dependencies between different instruments in a song. But again, you're not doing it in a way that the language model at the lowest level can just learn when this does this other thing tends, that when the drums do this, the bass does this. Instead, you're actually forcing that to be encoded inside the embedding. And so here's just kind of a sample from that model where I've separated out like a lead, melody, a bass line, and the drums. So that's starting to sound a lot more like a band. I want to play a few more examples because I actually just go to bed listening to these sometimes. Let's see. Here's a couple more examples of this. Okay, let me do one more. This is my favorite. Okay. There's a lot more that I would love to play, but we're running out of time. But okay, so that's. I was really excited to get those types of results, But again, coming back to like the original theme of this, that's just like pushing a button and getting something out. I mean, if you wanted to turn that into a song, like a talented musician could or a producer could take that and make something cool out of it, I think. So there's still obviously a level of human creativity there. But I think what's more interesting is actually be able to control what it's outputting and be able to teach it maybe. This model has learned kind of this huge space of music. That these are here are the things that I like, and so give me more of this. And maybe if you can't define what this is, and that's where this work that I did with Jesse Engel and Matt Hoffman at Google recently on latent constraints comes in. Although I have to say Jesse and Matt did most of the theoretical work, and then I applied it to this model. And this is on arXiv. I highly recommend you check out the paper. It's pretty awesome, and I can again say that because I only did a small part of the work. But the idea here is that instead of like interpolating between 2 points in the space, I'm just going to sample 1 point, but I'm going to teach a model how to take that point and turn it and shift it into some subspace of the latent space that I find interesting in some way. And we outline a bunch of different ways to actually do this, but you're basically training a GAN that the discriminator is saying, is this Z, this latent space code, is this in that space that I like? And then your generator is taking a Z, or we call it an actor, but it's taking the Z and shifting it. So it's just trying to shift it to the subspace that you're interested in. The other model's trying to identify whether you've succeeded or not, and they're actually working together cooperatively instead of adversarially to figure out how to do this. So an example of what we did with music is taking a sample out of this model that I just played, except in this case we're only modeling melodies, and train it on a couple of different rules to follow. So first I'm just going to play the initial prior example. This is just a random sample. I'm not going to play the whole thing just for time. But what you can see on the top here is that the red lines are basically showing where the notes are falling on the black keys. So they're outside of the C major scale. So what we did is we trained a model to be able to take a latent vector, and shift it into a space where it would only play within the C major scale. And so this is how it would shift that prior sample. So you should hear and see that it's very similar, but again, the key's been shifted. And then finally, we can also teach it how to increase the note density as well. So this is taking that original prior again and shifting it both into C and to a higher note density. So there's nothing special about those rules except that those in particular are easy to judge, so we're able to train it faster. But your rule could simply be listening to it and saying, oh, I like this one, I don't like this one. I mean, it would take, we'd have to work trying to get the number of examples that you would need to give it down, but it's definitely doable, and it's something that we're working on right now. Let's see what I have left. So I don't have much time to go into NSynth, unfortunately, but it's an autoencoder as well, using WaveNet to model audio. If you've heard of WaveNet, it's great work out of DeepMind, and we collaborated with them on this project. Yeah, I have to say I like the dog bone better. So yeah, I'll just play you some examples of this. It's a similar idea. It's much harder to model audio for all sorts of reasons, but we have this nice interface. You can go to g.co/soundmaker, and I am going to do the dog bone. So in this case, I'm going to show you starting with a trombone on one side and a dog barking on the other side. And then down here on the slider, I have it right in the middle, so this is going to be what's right in between those two. Right, so it's mixing, it's not just taking the two waveforms and like averaging them, it's actually mixing these higher level features that it's learned in its embedding space, or its latent space. and you know, you can shift it more towards the trombone side, or back towards the dog side, and get different results. Obviously, like, you know, musicians aren't necessarily interested in that example, but you can really find some amazing sounds in this by mixing instruments that you know would never have thought of before. And so there's this tool that's kind of more of a fun tool to play with, but we've also built an actual like Max for Live device which is like the software that people use who actually make music professionally, or a lot of them do, and it plugs right in and allows them to kind of explore these really large spaces of interpolations between instruments and get some really amazing sounds. So if you want to try that out, either one of those you could check out on our blog. So what's next? We're doing a lot of work on getting more data. So we're finding interesting ways to have people give us data, like musicians who are interested in helping out the project, as well as learning, figuring out how to take audio and convert it into a symbolic format. And we've had some recent progress on that, some successes with piano transcription. You know, we're working very closely with a lot of really incredible researchers in Google Brain, so we're trying to apply like the newest newest architectures to our work, and still working on these latent constraint models. And then finally, as you saw, a few of the examples I showed there were these nice interfaces. We did not make those because we are not, most of us at least are not great UI people, but there's a lot of great UI designers at Google who are really interested in this, and so we're really happy to collaborate with them. And we're also looking for more people outside of Google to help as well. And so if you're interested, check out our g.co/magenta for our blog, our code, all of that. So thank you very much.